And we're going to talk about modal models today. We have a very special guest, Bart Peters. He is the product line manager for the structures and environmental products in Siemens Digital Industries software, and he's going to talk to us about some modal models. So take it away, Bart.
Yeah, thanks a lot for the introduction. The next hour, I will try to cover following topics. We will discuss stabilization diagrams, quite important in the modal analysis process. Then we look a bit into the background of automatic modal parameter selection, a tool that makes it quite user-friendly, modal analysis. We have a relatively new method also that I want to discuss, the so-called MLMM method, or it stands for maximum likelihood estimation of a modal model. And then finally, a very recent addition to our software is the possibility to generate state space models from a modal model, and you can export as FMU and use it in your preferred simulation environment. I will talk about that. I also will try to give a few demos, so to make it a bit more illustrative and a bit more clear. Okay, so let's start a bit with an introduction. We are talking about getting modal models. This was the title of this talk. So we look into modal parameter estimation, and this is kind of a refresher. So what do we want to achieve? We want to essentially to curve fit our frequency response functions. So in frequency domain, or also sometimes methods work in time domain, then we need to curve fit the impulse response functions, which are the inverse Fourier transforms of the frequency response functions. And how do we do that, this curve fitting? We look a bit at the theory behind our measurements. So we know there is a dynamic system that generated these measurements with masses, dampers, springs. And we know that we can decompose these FRF measurements into a sum of modes. That's what this equation here on the left is illustrating. There are some parameters there that we need to identify, to estimate based on the measurement data on the left-hand side. And these parameters have a nice physical meaning, and they are in this blue box. So here in the denominator, you find lambda, and lambda is a complex number. It's a pole of the system, and a pole can be, is containing basically the damping ratio and the natural frequency of the mode as additional parameters. It's a complex number. You have also a matrix here, the A matrix, and that decomposes into a scaling factor and then a mode shapes times its transpose. So this is really the deformation of the structure at a certain frequency. There is a second part to this equation, because typically we don't see this mode shape full in as a second element. We have a mode shape and we have a participation factor. That's because we typically don't measure a full square matrix of frequency response functions. So when you have 100 accelerometers, you're not going to use 100 shakers, for instance, or when you hit a structure at 100 locations with a hammer, you're not going to use 100 accelerometers, but only a few. And so it's not square, this matrix, and that means that the mode shape is the most complete vector, but the participation factor is like only the mode shape at the locations where we do excite the structure. That's quite nice about it, because after the curve fitting, we don't end up with a mathematical equation. We end up with parameters that have a clear physical meaning: damping, frequency, mode shape. These are all very meaningful parameters that give a lot of insight into the structure. Here I try to illustrate a bit this curve fitting process by showing a single FRF. So this is a measured FRF, the red curve that you see now. We know this is the sum of several modes. And if you look at this curve, you would immediately see, okay, I have like 5 peaks. So there will be 5 modes in the data. The pink curve that you see appearing is kind of a theoretical curve of a single mode with a certain damping and frequency. And so I'm plotting it together with the measured data and also with an animation of the mode shape at that frequency. So this was a measurement on a vehicle, and you see there vehicle deforming at that frequency, basically. We have the similar curves for the other 4 modes that you see here. So this is the second one. It's a different deformation of your car. There's a third one, and you see maybe that it's quite clear that this pink curve is not very well aligned with the measurement data. But I will come back to that. We are really drawing now individual contributions of individual modes to the data. You have there the 4th mode, and this pink curve always have more or less the same shape. They have the same theoretical curve. Frequency and damping are the parameters. So if the damping is small, you will get a sharper peak. If the damping is big, you will get a broader peak. And then you have there a 5th mode. All modes have their own animation. And basically, it's not really visible, but there was a kind of a sixth resonance in the data, and the peak is a bit lower, but it contributes really to the measurements. And you see, it's also local mode, so it's only the roof of this car that is vibrating. Now that we have these 6 modes identified, we can take the sum of all these pink curves and then the green curve, and now you see that it's almost perfectly overlapping with the measurement data. So these 6 modes that you see here are explaining our data very well. So we extract all information from this data. And now you also see that this peak here, which was not very well curve fitted initially, or it looked like it was not very well curve fitted, by adding the tails of the neighboring modes, basically, so we kind of have to add all these pink curves together, we will see that we can really explain our data very well. That also means that when you do curve fitting, it's best to do it all together so that you identify really all modes in the data at once, such that you can also look at the cross influence of the modes in different frequency regions. That was a bit of an introduction what we try to achieve with modal parameter estimation. The process to get there is always the first question to answer: how many modes do I have in the data? And like on the previous graph, yeah, you can easily count 5 peaks, but there was apparently a hidden mode that you cannot easily see. So that's sometimes a bit misleading. So counting the peaks is a possibility, but be aware there are some hidden modes. These hidden modes sometimes appear when you have multiple shakers. So when you have 2 shakers, you can plot multiple mode indicator functions. And for instance, in the complex mode indicator function here, you see that the second curve also gets a peak. And that means that there is probably a hidden mode here very close to the first peak. And that's also what we saw on the previous slide. So essentially, it means here that there are 6 modes in this frequency range. And then we know in the curve fitting, we have to curve fit like 6 modes to the data. However, that does not always lead to good results. And that's how we came up, not only us, but in the early days of modal analysis, people came up with the concept of stabilization diagram. And that you see on this plot. And basically what we say here is we kind of give up on the idea that we do a minimal curve fitting of the exact number of modes. On the opposite, we really go to overestimate considerably the number of modes we may have in the data. And that you see here in this plot. So the y-axis is the number of modes that we are going to fit to the data. So the n, I called it, and the n comes back in this equation. So we are going to fit more and more modes to the same measurements. All of these models that we are going to fit appear on a horizontal line in this diagram, and they're all independent. So each line is independent from another, but you see when with an increased model order, we get always more and more modes represented in the data. And then we try to plot all of this information in a single graph, and that's what we call a stabilization diagram. And that's what you basically see here with all these colored characters. And if for instance, we start here at model order 11, we are going to compare it with the next model. So we fitted 11 modes. Now let's try to fit 12 modes to the data. Then we get the next line, and then we are going to compare the modes that we found in the 12 order model with the modes we found previously in the 11 order model. And we are going to assign a symbol and a color to our findings. So for instance, in model order 12, we have here like a new mode here that does not exist for 11. So it gets an O, a black O. That's a new mode. It did not exist before. Here, there is a D, a green D. It means this mode we found before, and frequency and damping are similar as in previous step. When you get a blue F, that's here for instance, it means frequency is similar as a previous mode, but not the damping. A V means frequency is similar and also the participation factor. And then finally, when you see a red S, that's really what we are looking for. Then that means that all criteria are kind of stable. So frequency, damping, participation factor, they're all very similar from the previous estimation. And so these are really the poles that we consider as being the ones that are the true modes, the true physical modes of our structure. The other ones that are a bit wandering around and not getting stable, we consider them not as really important for our structure that we measured. So that's a bit the concept of stabilization diagram. And typically you can go really very high in model order here. You can really exaggerate a lot and afterwards filter out the real things in which you're interested. Sometimes you get a bit messy results. Even the stabilization diagram does not show a lot of red S's. And this is a slide I made already almost 15 years ago or even longer. It's at the moment we developed Polymax. So this was a stabilization diagram from our earlier methods, the time end-of method. If you use the same data with Polymax, you get already a much nicer stabilization diagram where you easily see the modes. This was quite challenging data. It was a heavily damped vehicle that we tested here. We can take it also a step further. So because still as a user, you have to select kind of the red S's. So typically you take one red S per column because they belong to each other. They are supposed to represent the same physical pole. So you select a red S per column. But we also, to make it easier for the user, we also wanted to automate that. And that's kind of the next topic. It's the automatic modal parameter selection. And how did we achieve that? So basically, we were looking at so-called clustering methods. And I'm not going to explain this slide in detail, but these are kind of existing clustering algorithms that you find in literature. So each column represents a different algorithm to really group data together. And the dots you see on the screen are like data points. And these algorithms try to put them in groups. They all have slightly different results depending on how the data points are appearing in space. But they all kind of try to find groups. The idea is to apply these algorithms, or at least we selected one, and apply this to our stabilization diagram information and to find then a representative pole of such a cluster. So for instance, here you clearly see three clusters, a green one, an orange one, and a blue one. So these are probably three poles, and then we select like a representative somewhere more or less in the middle of such a cluster. This is further illustrated here on our data. So here we get our typical view of a stabilization diagram. We get frequency versus model size. First, we are going to take a different look at the stabilization diagram. So we keep the frequency axis, but instead of model size, we are going to plot the damping ratio of all these modes that we see here as dots in this diagram. And then we end up with such a graph. So this is essentially the same information, but plotted in a different way. Now you don't see the model order anymore, but you clearly see now clusters of stable poles. And so to this, we typically don't show in the software. It's a bit behind the scenes that we do this, but then clustering algorithms work on this type of information. So we are going to group the data in clusters, and you see it's maybe not that a difficult job here when you see these quite distinct clusters. And then we are going to select a representative for each cluster, which is the pink cross. And that's how essentially our automatic method works. So here you see it illustrated in the software. So it's an add-in to modal analysis. It's automatic modal parameter selection. Then you need to hit the button, select poles. And so that's basically what happens. So in the software you find poles automatically selected, and poles get kind of a label AMPS. That means it has been automatically found by the algorithm. So automatic modal parameter selection, essentially it's applying clustering algorithms to the information we find in the stabilization diagram. The next step, this will take a bit more time, is to look into a new method, and I will also give a demo of that method, the so-called maximum likelihood estimation of a modal model method, MLMM in short. This method was recently developed, and you could wonder, why do we still need another method? Modal analysis exists now for maybe more than 40 years. A lot of people have been working on algorithms, improving methods, making them faster, making them better. But still, we observed that people also try to apply modal analysis to more and more challenging structures and challenging data. And that's a bit the explanation behind the fact that we always need to evolve the technology as well, because the data get more and more difficult to analyze. And more in particular, we were having some trouble curve fitting data that had a large number of references, a lot of excitation locations. And a typical case was for acoustic modal analysis, and you see a typical acoustic mode shape here on the right. So it's like vibration data, but you replace an exciter with a loudspeaker, and an accelerometer, you replace it by a microphone. But the methods and the ideas behind are essentially the same. But for acoustic modal analysis, you have to use a lot of loudspeakers, a lot of loudspeaker locations, and sometimes even 10 or more to get a nice excitation of your entire cavity of the car, for instance. And that caused some problems in curve fitting this data. The same is true for trim body, so highly damped car bodies. Also there, we need to apply a lot of excitation points to get a decent modal model. And so that was some of the reasons why we developed a new method called MLMM. In some cases, we want to get real modes as opposed to complex modes. So complex mode shapes, they show a kind of a wave propagation. Real modes, they show more standing wave behavior. And so, for instance, for correlating your measurement results with finite elements, sometimes real modes are preferred. They're also a bit easier to interpret. The method MLMM also allows to do a better job in getting real modes as opposed to the earlier methods. I will come back to that. And the same is true for a reciprocal model. That's in some cases also important for modification prediction, hybrid modeling, body flexibility studies on vehicles. And in the previous methods, both real modes and reciprocal modes were kind of a post-processing step, which would degrade the quality of the model. Now with MLMM, we embed these constraints into the optimization and we get much better models, much more representative for the data. The MLMM method is an iterative method. It can take some time, depending on the number of iterations you request. But every step is kind of goes relatively fast. It's like a Polymax step, but you repeat it over and over. You would also need Polymax to generate starting values for the method. So because it's like with any iterative methods, you need kind of initial values, so starting values. And then you refine these values, you make them better and better to more closely match your measurement data. That's a bit the idea behind MLMM. Maybe still a bit the issue with these reciprocal modes that you see illustrated here. So on the left-hand side of this graph, you have kind of a modal model of a trim body that is relatively well explaining the data. But when, as a second step, you would make the mode set reciprocal, you would suddenly lose quite some quality in the curve fit. And you would see here, like this blue peak suddenly appears. The blue curve does not represent the data very well. With MLMM, we can build in reciprocity as a constraint from the beginning, and you end up with a very nice curve fit, even though you impose some additional constraints to your model. And the same holds true for real modes. Also there, you sometimes saw a degradation of the curve fit after making your modes real. This can also be embedded in the MLMM method. So what is MLMM essentially doing? So first, we need a Polymax step, as I explained. So we get initial values for the poles, mode shapes, participation factor, and also upper and lower residuals. And then we are going to do some iterations. And the idea behind this is to minimize in each iteration the differences between the measured and the synthesized FRFs that you see expressed in this equation. So the synthesized FRFs, that's the equation I showed in the beginning of this presentation. You have a sum of modes. You have also the lower and the upper residuals, modeling the out-of-band modes. With all this information, we try to model the data. So we get synthesized FRFs. We compare them with the measurements, and we calculate kind of what is called a cost function. We kind of sum all these differences over the number of outputs that we have, so the number of accelerometers, the number of shakers or inputs, the number of frequency lines. So we really look at the global error between the measurements and our current model. So we take the absolute value squared. We can also, if we want, apply a weighting factor, depending on the noise you have on the data. If you have a lot of noise, it will contribute less to the cost function. If the data is very reliable, there's almost no noise, then it's an important part of this cost function. And so that's based on this equation, we managed to get some iterative equations. And in each step, we slightly modify frequency damping mode shapes to get closer and closer to the measurement data. And that you kind of see illustrated here. Here on the y-axis, you see the value of the cost function. So it's really these errors that we have still. And with each iteration, we decrease the errors until we reach convergence somehow. In a minute, I will go to the demo, but maybe show a bit the process before. We are quite familiar with this. This is Polymax. We have the stabilization diagram, what I just explained. We did AMPS, so we found all the modes here in an automatic way. Then based on these modes, we can do MLMM iterations. So we start from the set of modes. In this case, we applied 30 iterations, and it's still converging. So here you see that cost function in the software. And at the end, we get an optimal fit of the data. So here you see two FRFs, where the green one is the measurement and the red one is the curve fit. You see it's still not perfect, but if you compare it with what we had initially with Polymax, you would see quite some improvement, and that's on the next slide. So this is the initial curve fit, you could say, with Polymax. So it's quite okay, but yeah, it can be improved. So with MLMM, we get these results, so especially the first FRF, is very closely matched with the synthesized FRF. And without increasing the number of modes. So we just take the initial number of modes from Polymax, but we are going to improve frequency damping mode shape to get closer and closer to the data. So what's happening behind the scenes? So we only show this, the cost function, so you see it decreasing. Behind the scenes, there is also kind of every iteration, we are slightly modifying the frequencies, and you see them here aligned in 10 iterations. With damping, it's typically a bit more spectacular. The damping values are changing much more during these iterations. We always are closer and closer to the measurement data after a few iterations. Yeah, so now I will switch to the demo. I opened already a database here in Testlab. It's a car without a roof, a convertible car. So quite flexible, quite some torsion you will see. Let's go to the data. So we have like 375 accelerometers on that car, and we had 2 shakers, 2 locations. So we have a 375 times 2 FRF matrix that we are going to analyze. You see the sum of the FRFs here at the top. Let's first go to Polymax. Now I'm showing the complex BIF, so I have 2 curves because I have 2 shakers. You also see that above 34, 35 Hertz, you start to get quite noisy data. So let's limit the analysis between 2 and 34.7 Hertz. We are going to calculate a stabilization diagram. That's done, so Polymax is done. We are going to use the automatic pole selection button, and we end up with like 21 modes. I can now do the mode shapes from Polymax. And you can see how they move. So the first modes are more a bit rigid body modes, but then we start to see some deformation modes of this car. The block you see moving a lot here, that's the engine. So the engine was also measured, but as you know, the engine is quite flexibly suspended in the car. So it moves a lot. And you see a lot of torsional behavior in this car. We can now also do some further MLMM steps. So that's the additional tab that you find here. So now we take these same modes, they will appear also here, and we can do some iterations. So now I put 20 iterations. I will give them a name, the modes that I will generate at the end, and I will push the calculate button. So now you will see this cost function. Every iteration we add information. And you see that the cost function is going down, but after a few iterations, we start to see some convergence. So that means that we are still improving, but not so much anymore. So let's just finish here the 20 iterations. Okay, that's done. So now here I have now my new modes, and you see that they are still there, but like the second one hardly changed. Still 2.21 damping, but the first one, for instance, went from 1.34 to 3.48 damping. So in general, the damping increased a bit for most of the modes. Let's now see a bit at the results of the curve fitting. So these are the MLMM results. So this is the last processing I did, demo MLMM. You see that the correlation is very good. So between the measured data and the synthesized data, 98% correlation. Let's compare that with what we had before with Polymax. That's the demo Pmax data. So also there it was quite okay, 95% of correlation. So we could further improve it with MLMM. Maybe there is, like these ones, they are a bit lower, 88 and 84%. That's the second row. If you now go to MLMM, you see that again we reach 95 and 98% of correlation. Yeah, in terms of mode shapes, they will also be different. So if you compare MLMM mode shapes with Polymax mode shapes, calculate the MAC value. You see some diagonal elements, so some modes come back, but some of them can be quite different. Although here it's reasonable, so there are some changes in mode shapes, but maybe not too dramatic. Yeah. So left you see the MLMM mode, right you see the Polymax mode. I'm going just to show a few of them. But overall, the data is better explained by using the MLMM method. So that concludes the MLMM part. Yeah, because I illustrated MLMM on a vibration case, I also have some results from an acoustic case where we use a grid of microphones. You see them here. We use loudspeakers. Total, we had like 10 locations of loudspeakers in this car. Here you see some of the FRFs. So this is always the same microphone, but looking at the 10 different FRFs from the 10 different loudspeakers. So you see a lot of damping in this data. Nevertheless, we found quite some modes with MLMM, and you see these acoustic mode shapes animated on this slide. So you really see these standing waves inside the car body. So this concluded the MLMM part. Now let's go to the last part. So now with MLMM and all the things before, stabilization diagram, AMPS, we generated very reliable models of our structure that we tested. So now we want to use these models also in combination maybe with other simulation models or in a kind of a forced response analysis way, or we want to make use of the modal model inside or outside Testlab. And that's why we came up with this state space modeling concept and the export to Matlab or the export to FMU. And one of the first cases we encountered to make use of this functionality, well, it's a bit of a busy slide, but in essence, what this project was about was it was an existing car, so a vehicle body that was already on the market, but the damper company wanted to add another damper to an improved version of their initial damper to the shock absorber to existing car. And so they were kind of making physical models of their damper or their shock absorber using AmaSim, so Simcenter AmaSim, trying to optimize the behavior of the shock absorber. But they also wanted to know how the damper would work in combination with the vehicle. And the vehicle, they could do measurements, or they asked us to do measurements, but they didn't have any simulation model of that car because it was not there. They didn't build the car; it was from a car manufacturer, obviously. And they also wanted to use the most reliable model, which is essentially a measured model. So they did measurements on a car body using the attachment points of the physical damper as excitation points, and then looking at some typical target locations in the car. So there was accelerometers put on the seat. There were also accelerometers at the damper points, and there was also some sound pressure measurements done at the right ear and the left ear driver, because these are also important targets. So these transfer functions, the idea is now to combine these transfer functions with inputs from a modified damper model. The transfer function as such were not directly used, but a model was derived from them using modal analysis. So we did Polymax, we did MLMM, and then we generated a state space model so that people could do time domain simulations even and even listen to the results of the new damper. So by synthesizing the sound pressure levels based on the new damper and the body model, you could really hear what was going on. It will be illustrated also with a demo of these concepts. What is the idea here? The idea is to take a modal model, as I was explaining before. So we have mode shapes, natural frequencies, damping ratios. And we want to put that in a model that also can be used in other environments. And then the state space model is very well suited. It's a kind of an input-output model. So the U that you see here is the excitation of the model, the input, and the Y is the output, so the response of the model. There is also kind of an internal variable, the X, and that's the state. And typically, yeah, that's an internal variable. We don't know exactly what it is, but it's needed to run the model. There exist two variants of the model, a continuous time model and a discrete time model. Here you see, for instance, the derivative of the state variable. The discrete time model is a bit simpler because these are just recursive formulas, and this is a bit more logical for measurements. There you also have a certain sampling frequency, so your data is sampled. So you have the samples of your input, and you can easily calculate your output of the model. It's just a recursive formulas. Here you would need some time integration methods, so that's a bit more complex to solve. Discrete time models are a bit easier. And so the challenge here was to make a data-driven model that people could use as a component in an integrated simulation environment. Maybe like in my example, the shock absorber existed as a physical model, but I wanted to couple that to a data-driven model of the car itself that you could do with a state space model. So what we do, we take an existing mode set and we convert it to a state space model, and you can share it in your organization in a standardized format. And the export that we offer is either MATLAB or as an FMU, following the FMI standard. I will also explain a bit what that is about, functional mockup unit or functional mockup interface. What are the benefits of this solution is that we will generate reliable models that are closely representing our measurement data, thanks to the stabilization diagram interpretation, MLMM. So we have industry-proven solvers. In the software, you can also check the quality of your state space model before exporting it and passing it on to a colleague, perhaps. So you're quite sure about the quality of your model. Maybe a little bit of theory, because at first, these two models look quite different. So you have your modal model, you have your state space model. How can we put our modal model into this ABCD model? Because these are the parameters, matrices A, B, C, D. However, if you take a closer look, we can already see much more similarities. So when you take this theoretical model ABCD, we can do an eigenvalue decomposition of the matrix A. That's standard mathematics. We have eigenvalues, we have eigenshapes, an eigenvector matrix. We then do a coordinate transformation by taking this eigenvector matrix. And then we have kind of a different model, but with exactly the same input-output behavior. So the input is still U, the output is still Y. Only the internal matrices changed. They're not A, B, C, D anymore, but lambda, phi minus 1 times B, C times phi, and D. If we now take this form and we apply the Laplace transformation to that, to this analytical model, we get a representation in frequency domain. We now get a kind of a transfer function where we have all these matrices of the model. And now we are already very close to what we get in Testlab after modal analysis. But rather than taking this summation, we can write this equation down in the matrix format. So you have a diagonal matrix of all your poles. You just put your mode shapes next to each other. You do the same for your participation factor. And we end up with this equation. If you compare now both forms, you see that large part of the job is already done. It's like this C times phi matrix, that's just our mode shapes. The phi minus 1 times B matrix, that's our participation factors. Our poles are identical here. We just have here a bit of troublesome terms, the lower and the upper residuals. And they are quite important to include. They do not easily transfer into a state space model. So the trick that we will apply there, and you will also see it in the demo, is that we are going to substitute these lower and upper residuals by some artificial modes that are far away from our frequencies of interest. And then we can include them in this general part of this equation. And then we can do the mapping on a state space model. That's a bit the idea. Here you see a bit the illustration of this state space modeling concept and the replacement of the lower and upper residual by some what we call residual compensation modes. So let me go through this graph. So the red curve is a measured FRF, as you can see. The green one is what we would do in a traditional way with modal analysis. So we have good representation of the data inside the frequency band. But we also need to include some lower residual behavior and some upper residual behavior to really model the dynamics of the modes outside the band within the band of interest. So outside the band, of course, we didn't look at this data. We only looked at the effect of the modes inside the band. And so we need to include a residual, and the same for the lower frequencies. Otherwise, we would not get a nice fit. With the state space model, we cannot just take the green synthesized FRFs. We need to change a bit the lower and upper residual formulation. And you see here a mode appearing, a kind of a highly damped mode at lower frequency. There is also a mode at higher frequencies. But overall, the blue curve and the green are closely matching each other, especially in the frequency band of interest. If you would just ignore this lower and upper residual, because it's a bit difficult to model maybe, you would end up with the pink situation. And so you see that the peaks are maybe there, but you see that overall, you don't fit the data very well in your frequency band of interest. So you really need these out-of-band compensation modes to get a realistic representation of the data in your band. So that's why we paid quite some attention to these. What are the applications? So once you have a model, you can use it in time domain and frequency domain for simulations, for control studies. You can do forced response analysis, so you can apply an input to your state space model and calculate the output. It's used in structural coupling. That was a bit a damper case I showed before. Substructuring, virtual sensing is a potential use of the method. And why did we select state space models? Because they're kind of a reduced order model. We only have a few parameters, A, B, C, D, and we represent a whole set of FRF data, basically. As I said, you can use it both in time and frequency domain. You have also two flavors. You have a continuous time model and a discrete time model. And it's also possible to change even the quantity. So you can go from displacement to velocity to acceleration based on some theoretical derivations. In the software, I will do first the generation of a state space model. I will export it to an FMU, and then I will load the FMU in Testlab and do some simulations, some time domain simulations to illustrate what we can do with these models. So if you're interested to know more about this FMU, so it's not a Siemens invention, it's a standard that people use to exchange models. And if you take a look at this website, oh yeah, here it is. So here you see a list of companies that are supporting these FMU standards. So everybody is there basically that is generating models. And these FMUs allow to change models and use models in a different environment. So there's like 170 plus tools that are supporting it. So this is a website maintained by a committee behind FMU. Okay, so now it's time for a demo. I will open a different Testlab project. Okay, let's maybe take the right data. So this was, the geometry is not really appealing. It was just a tube, and it was not really a modal test. It was an environmental test, vibration control test, where we had a shaker exciting a tube with some sine sweep excitation. But it's a nice example to illustrate what we can do with a state space model. So there is like 10 accelerometers and one output. It's also not a force measurement, it's a voltage that we send to the shaker. That's typical for environmental testing. So it's a G per volt transfer function. We are more used to G per Newton, but that doesn't really matter. It still has modes, it has dynamics, so we can still do modal analysis here. Here you see the complex MIF of the data, all the peaks from 20 to 2000 Hertz. We go to the stabilization diagram. We find a lot of stable poles, so let's select them. Sometimes you have to be a bit careful. You can also, if you observe that the automatic selection was maybe not perfect, like here, for instance, when you zoom in, you would see that you have two modes. So I can select a second one here, because it's clearly there. Now I can calculate the mode shapes. And then we can have a look already at the synthesis results. You see that it's maybe not great. So you see the green curve is not really on top of the red one. Maybe for some others it's a bit better. But yeah, this is not yet a good quality model, I would say. So let's really go to MLMM and use 100 iterations to really improve it a lot. You can always stop the iteration if you think you reached convergence. So now we are at around 30 iterations, 34. And yeah, maybe it's not changing too much anymore. So we can stop it. And we can look at the improved synthesis now. And now we see a very nice fit of the data. So the green curve is almost perfectly on top of the red one. Yeah, maybe not for all FRFs, but at least for the most important ones. We get a very nice representation of the data. So now let's generate a state space model. That's also an add-in. I already activated it, but you have state space model conversion. When you activate the add-in, you have this state space model checkbox that you can switch on. And it's immediately calculating the state space model. So that's the blue curve you see appearing now. And it's almost perfectly on top of the green one. Here you see the parameters that influence the model. So maybe if I take the defaults, that's the default model. So you see blue and green are maybe not perfectly on top of each other. So it's possible to play with the parameters. And especially here, this situation can improve by taking a bit of lower damping for this compensation mode. So it's really possible to play with it. So we have a continuous time model and a discrete time model, as I explained before. For the discrete time model, we need to select a sampling frequency. And the default here is 50,000 Hertz, so it's way above the frequency range of interest. And that's also needed. We go to 2000 Hertz, but we put an upper residual mode at 5 times higher, so at 10,000 Hertz. And then it's also recommended to sample the model again 5 times higher. Let's check if we take a lower one, 25,600, whether we are still having a good model. That seems to be the case, so the blue curve did not change too much. We get a warning though that we are a bit low. But it's interesting to see the effect of sampling. So if you're really exaggerating and taking the sampling frequency here in the frequency range of interest, so if I take, for instance, maybe 1200 Hertz, you will see that we get a very bad model. And you even see the aliasing around 1200 Hertz. So that's the model is mirrored around that frequency, and it's completely not representative for the data. So that's why we have this functionality here to really generate a discrete time model rather than generate a continuous time model, pass it to a colleague that need to discretize it. But without knowing the frequency content of your data, it's a bit tricky. So that's why the conversion can be done also here in Testlab, so that you're absolutely sure that you get a very high quality model. So if you again take 25,600, I'm representing very closely my data, and I will have a good model. So I can store it as a FMU of Matlab, as I said before. So let's maybe do as an FMU. Yeah, there is already on the preparation my FMU. Okay. I will close now Testlab modal analysis, and I will go to the process designer to illustrate the use of an FMU. So it's not modal analysis. No, channel processing, process designer. I will open the same database, but now in process designer, Testlab Neo. So I made this process with the FMU loaded here, but I can maybe illustrate what's happening. If I take a new block, FMU, it's an empty block, but here I can import an FMU. And if I now take the FMU that I just generated, demo, I can open it. And here we can inspect the model. So there is inputs to the model. And you see here we have the Testlab names appearing here. We have to map it. Maybe you can change the name here, put a different DOF ID here. And it will be important because we will excite the model, and the DOF ID need to correspond to the DOF ID of your input. You also see your outputs here, where you have all the Testlab DOF IDs, and the units are also there. Okay, so I did it here. I already did the mapping, so I changed this name into time series, a DOF ID corresponding to a time series I have in my database to be able to excite my model. So I can delete this one. What is also important is that we excite the model with data that has the same sampling rate as the model. And in Testlab, I showed modal analysis that we used a sampling rate of 25,600. So we need to make sure our excitation is at the same frequency. So that's why I have this resampling block. Then I go back to the original sampling rate, 6,400, and I will calculate the spectrum. So the spectrum that comes out of my model and the spectrum that is directly coming from the data. Let me load this into input basket. SVSW1. And now I need only to load the relevant time data that corresponded to my model. I will not use the strains. Voila. Input basket. So now I loaded like an input, so a drive in voltage. That's the one we can see here. So it's a voltage that is driving my model. So it's exciting my model. It's a sine sweep in voltage. And we will calculate the outputs. At the same time, I will split off the other channels here, which are the responses, the measured responses. as you can see here illustrated. And I will also calculate the spectra from these. And I can then compare the spectra from the responses measured with the responses coming out of my model. That's a bit the idea here, to illustrate that we are quite close to the data with this model. So now let's run the FMU. Everything should be in the input basket. So I push run. I forgot to give it a name, but that's fine. I think it will take 10-15 seconds or so to run. The data can be seen here. So we now have like every time 2 time series. So if I take a different view and I click here, you see, for instance, the simulated data from the model compared to the measured data. So you see the time domain, they are quite closely matching with each other, all these channels. So the model that we put here in between is able to generate time data that really is almost the same as on the real structure. In frequency domain, though, you would see some differences. So maybe this one is So at lower frequencies, you see a very good match between the data and the model. At higher frequencies, you start to see some deviations. One of the reasons is that the model was generated using low-level random data, and now I'm trying to simulate a high-level sine sweep with this model. But you see that this FMU is really able to take a model, and you can use it as it was, like a real structure. So you can excite it, you can drive it with this voltage here. So that really the time domain excitation we use to excite our model. So you see a sine sweep excitation here. And the model will calculate, we will calculate the responses of that model here in Testlab Process Designer. Okay, so if I go now for the final slides. So again, this example I explained, we also run that, and that's a bit what you see here. So we have a very good model of the data. We put it in a state space form. And now if we take the damper loads, the shock absorber loads, the forces, we can excite our model with these dampers. And we can calculate, for instance, here the sound pressure inside the cavity of the car by using this modal state space model. We tackled the stabilization diagram, the automatic interpretation of the stabilization diagram by these AMPS methods based on clustering. And then I also highlighted the MLMM method, so a kind of advanced solver that improves the model and it gets closer and closer to the data. And then finally, I illustrated the state space modeling concept, so you can generate a state space from modal analysis. You can package it as a MATLAB model or as an FMU and use it in your preferred simulation environment.